oxide, hydroxide molecule, sometimes that hydrogen will just be like, you know what, screw you, I'm going to go make friends somewhere else. But it has to leave its electron behind. So it's just an H plus floating around in water. And as long as our H pluses equal our hydroxides, it's still just pH 7 neutral water. But if we add too many hydroxides, we get a base that can burn you, like lime. You get too many H pluses, you get an acid that can burn you, like hydrochloric acid. The names of the most common ones end in ate, one less end in ite. The exception of those being these weird guys, cyanide and hydroxide. If you add an H to a polyatomic ion, the only thing it does is add 1 to its charge, but it's still named the same, right? So here you have hydrogen carbonate, right? And what do we call this? Add carbonate plus H, bicarbonate, or hydrogen carbonate. If you add an H to a sulfate, what do you have? Hydrogen sulfate. Halogens can form polyatomic ions with oxygen. They always have a -1 charge. Please note, I should point out, because we noticed that on that table back here, all of the chlorates are always -1. Sulfate is -2. Sulfite is -2. Phosphate is -3. So these polyatomic ions are not always -1. All of the halogen polyatomic ions are -1. But the sulfates and phosphate, like nitrates, you're just going to have to know their charges or know where to look it up. Right? Perchlorate, like hyperchlorate, has more, 1 more. Chlorite, 1 less. Hypochlorite has even 1 less than that. What's the common name for a hypochlorite solution? I guarantee you know this. I think it's sodium hypochlorite. Yeah, bleach. You use hypochlorite all the time. Well, you might not. I never really bleach my whites. I use it a lot at work, though. It's a good sterilizing solution. Don't
also
drink it.
destroys DNA, so if you need to hide the body.
Sure. Ammonium is another good denaturing denaturing thing. Which you either know because science or because you watch. Yeah, actually, there's a lot of shows out there that probably teach you that. Yeah, like want to cover up want to leave a blood stain but have it not be incriminating. Spray it, but still leave it red. Then use ammonia. You want to just get rid of the redness, then that's when you need the bleach. Slightly off topic. All right, so we have a lot of shows about psychopaths on TV right now. Like Game of Thrones. 90% of those characters are, at a minimum, sociopathic.
Or CNN.
So, yeah. When we're writing these things out, the same rules apply. Nitrate ions, you can look up the charge. So if we're trying to have magnesium nitrate, what's that going to do? Nitrate has a charge of -1 as a polyatomic ion. Magnesium is going to have a charge of +2, right? So what's the chemical formula for magnesium nitrate? MgNO3. We put that NO3 in parentheses because we're treating it like it's one other atom, like it's one non-metal, right? So it's a polyatomic thing, but it's a unit all in and of itself. We do not write MgN2O6. Do not do that. That is a fundamentally different molecule. This is like, this right here is like me taking 2 football players and taping them 1 to each arm. That is very different than me taking those football players, dismembering them and attaching their body parts all over you. You know, just to stay with the whole Dexter theme. Yeah, that works for that works for this, yes. With the nitrate as both the beginning and the end in this case, because the magnesium is the one in the middle. So, we put NO3 in parentheses and then a 2 after that. Because we are treating this NO3 as if it is one unit. And we need 2 of those units to make magnesium nitrate. Everybody follow? What's the formula for aluminum bicarbonate? Before I advance on, somebody do it for me. What's the charge for aluminum? Positive 3. So how many bicarbonates are we going to need? Well, if we wanted to be really thorough, we'd look up the charge for carbonate, right? This is aluminum bicarbonate. So what's the charge on bicarbonate? -1. So how many -1s do we need to balance out a positive 3? We need 3 of them. So that's +3 here. A bicarbonate ion is a carbonate ion that already has a hydrogen attached, right? With a charge of -1. So we need 3 of these guys, right? So what's that going to look like? Aluminum with bicarbonate in parentheses and a 3 after it. Because we need 3. Aluminum +3, bicarbonates -1 each. We need 3 of them. Aluminum, HCO3, 3. Be careful with your parentheses. On the exam, you're not going to be writing this stuff out. So hopefully I have been careful with the parentheses. But that's what it's going to look like. Once again, this is not AlH3C309. That's a very different molecule. Na2SO4. What's the name? The metal is sodium, and the ion is sulfate. Now you'll note that it's still sulfate and not sulfide. Why not? I thought for these ionic compounds we change it to ide. But if it was a sodium sulfide, what would it be? It'd just be NaS, or technically Na2S, right? So we have to keep these polyatomic ions, they keep their name. But we all know, because we're so familiar with these names, that sulfate, phosphate, hypochlorate, that these guys are polyatomic ions, right? Sure. FePO4. That's a phosphate. There's 1 of them, and if we look it up, it has a -3 charge. So there's 1 iron atom attached to it. What does the charge of that iron atom have to be? +3, so it's iron 3 phosphate. Right? This is just a matter of remembering sodium only comes in one way. Iron can come in multiple ways. So you just have to remember, anytime you're naming an iron ionic compound, you have to name which charge it has. Question?
So just making sure, like, there's always going to be like oxygen when it comes to naming compounds that are polyatomic.
Well, except ammonia,
Okay.
which is NH4,
Right.
or hydroxyl, which technically still has oxygen, sure. Most of them are going to have oxygen, yes. Sometimes, and usually quite a bit of oxygen.
If it was iron 2 phosphate, what would it be?
Good question. If this was iron 2 phosphate instead of iron 3 phosphate, what would the chemical symbol be? What would the chemical name be? Well, iron 2 has a charge of 2, right? Phosphate has a charge of 3. So that means that our smallest common denominator between those two is 6, right? So we would need 3 iron 2s and 2 phosphates. So it would be iron 2, 3, parenthetical PO4, 2. Everybody follow? Question?
Okay, if we're gonna answer this online, do we need that square?
No.
Like, I'm just trying to figure out, like, how we
The-
write out
the-
this answer.
The square, well, for one thing, once again, on the test, it's going to be multiple choice.
Oh,
The square here is just to show you this is the thing. So if I were to ask you, it would be name this compound. And you would need to recognize that PO4 is phosphate. So then you would go, well, that's iron, phosphate, but remember, iron has multiple charges. So you know the charge of phosphate, and you have to calculate, therefore, which iron it is, and then the name that you would pick is iron 3-phosphate.
so we wouldn't type this out at all, we would just
You would pick
multiple choice?
C.
Okay.
Because C might be iron 3-phosphate, and B might be iron 2-phosphate. And D might be iron 3-phosphide, which you would know is not a thing. You wouldn't pick that one, right? Or it might say, it might be a true or false question.
But there's nothing where we're gonna like type it?
Not on the exam, no. Homework, when there's only maximum 12 questions, that I'm willing to go in and double check. I'm not double checking 48 questions on all y'all. That completely defeats the purpose of doing tests online. At that point, I should hand them out to you so I can check your work and give you partial credit for your work, right? Like, there are pros and cons to both of these. So no, test is going to be multiple choice, true, false, sort of matching. Sort of matching. I don't think in this one, but there might be matching questions on a test. And if that happens, then everyone will get the matching question. But then which multiple choice, true, false ones you see, out of like the 80 some odd questions from chapter 2, you will see 12. And you will see 12. And you will see 12. And between the three of you, there might be 2 that are overlapping. And for you, it would be number 2, and for you, it would be number 9, and for you, you don't have any of the same ones, sorry. Like that's, because it's all random, so. Question?
How many questions for each chapter?
An even number of questions to get us close to 50 without going over. So, if we finish chapter 6 today, 12 of each for a total of 48. If we don't, there will be 16 of each for a total of 48, or something like that. Did I do that math right? I did that math right. It would go up. So it's just, so if we have, if you have 5 chapters on a test, then it'll be 10 questions each. So it's going to be about 50 questions, evenly distributed across all the chapters.
And it's gonna be chronological, or it's gonna be just like that?
I'm pretty sure it's going to be chronological by chapter, but within the chapter it'll be random.
Okay.
So your chapter 2 questions will come first, your chapter 3 questions will come next. I think, because I know that it will randomize within the chapters, I do not know if it randomizes your whole test. I will tell you this, if possible, it will randomize your whole test. I don't think it's possible. But within each chapter, yes, you might get a question from the end, and then one at the beginning, and then the middle, and back to the beginning, and right. It's not going to be, here's a question about 2.1, then here's a question about 2.2, no.
I just keep them searching for all these things you asked.
Yeah. You'll be fine. You know more of this than you think you do, if you just give yourself credit. And then the rest you can look up.
Wait, we just give ourselves credit?
Mentally.
I can do this.
Think positive. Calcium carbonate, calcium sulfate. We make plaster casts out of calcium sulfate. We make antacids out of sodium bicarbonate. This is another one of those things. Aluminum phosphates in it, we make antacids out of it. Barium sulfate for contrast in X-rays. Blah, 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 blah. Epsom salts, magnesium sulfate, for sucking out all those toxins, supposedly. Really just for making a really highly osmotic solution to force a lot of water out of your system, hopefully bringing other ions with it too. That's all that Epsom salt that does, really.
You can make it into many different things.
Yeah, sure. And you could, well, yeah, it helps for a lot of things. I'm not bad mouthing it like it doesn't have a purpose in the same way that, like, you know, take aspirin and it helps, but it's just one thing and it has a really simple function, but it does not cure everything, right? So it's just like, really simple things can do good things. It's just, it's not magic. It's chemistry. and biology, which is chemistry. So it's the same thing. 6-5. We're coming up on 7:30. Do we need to take a break?
Yeah.
Let's take a break. Bathroom, stretch your legs. Whoever hits the door first, flip the light, please, so that it's brighter, not darker.
10 minutes?
Yeah, 10 minutes.
How many minutes?
And all of our tests are taken on.
You can take wherever it is that you have a reliable internet connection. And I would not suggest you do it on a tablet. Good. And if you need to, I think you can go to the testing center. You can go to any computer lab here on campus. You just can't go to the study center and have them help you with it. You might even be able to go there and say, can I use that computer back there? And they might even let you do that, but they will not sit there with you and walk you through all of it.
So why not take it on this?
Stability issues. And I honestly don't know if that's a problem with D2L, but I know that it was a problem with both Blackboard and Canvas, that stability issues between the app version, the tablet version of the integration between those two softwares. It can cause hiccups where certain questions don't get saved, or you lose connection, and then some of the answers weren't saved, or...
That's weird, I've taken everything on this and never had a problem that I know.
Well, then D2L might have a much better integration.
I think it'd be worth mentioning to the class
What's that?
that when you're taking one of these exams and you click your radio button, and then you're trying to scroll down to the next question using this wheel, if the radio button is still focused, it changes your answer. And you can
It rolls
submit
it.
that. Huh?
It rolls it.
Well,
Yeah, because what you're doing is you're telling it to select this subsection, and then when you scroll up or down, it's just scrolling the answer. That is actually, yes, that is worth mentioning. So in other words, either be really cognizant of what you're doing, or just be really careful with your scroll wheel.
yeah. Click the radio button, click outside of the radio button, and then
Right.
scroll.
Yep. That's the thing. So, or just don't use your scroll at all, and just always grab the bar on the right. But yeah, I imagine that's, but once again, that would actually make an iPad slightly superior, because you're not, like, you're always pressing the option that you want.
Well, you're also using gestures though to scroll, and depending on how,
Yeah, I don't know how that would
depending
work.
on how they've handled that event. Isn't that lovely? I sent my mom just beautiful flowers.
Teach my kids to do stuff.
Well,
I understand.
anemic.
Yeah, I understand why
Those are
we
red
get
tulips.
flowers, but and I like getting them too, but at the same time, there's like this
Broken.
fundamental thing where I'm like, why do we celebrate life by handing people dead things that we just killed to celebrate? I mean, like, it would be similar to be like, here's a fresh steak, I just butchered it myself. And most people are like, that's a really weird gift.
That's awesome.
But yeah, you know,
let it age.
some people might be really excited by that, but there's also like, these two things are not equal. Like, yes, they are. You just took a living thing and you just killed it, and we're gonna celebrate life by watching it slowly die because it doesn't have roots anymore. Like,
And it costs a ridiculous amount.
Yeah.
And the only way I found to resolve all those questions in my mind is that as soon as she gets it, I'm gonna get this squealing call from my mom,
right? No.
and she
It's-
loves it.
Sure.
That's
It's the same thing about, you know, it's like anything else. If people like it, then get it for them because they like it, not because there's an inherent value in the gift.
So is our test under quizzes then?
It'll pop up quizzes, because there isn't
Those
a
part
tab
that
for
data,
exams. But yeah, it'll be labeled as an
yeah.
exam in the quizzes content section.
So is the one that always
It's
failed?
probably what you for me to
I had to
get
take it multiple
accommodations.
times just to get through.
Was that too late?
Mine says-
I don't think it's too late, but it would be too late for you to get accommodations for the test that opens tomorrow.
Intermediate.
Yes.
Did
I
you
did
do
get
mine?
I have not yet, because none of them have been
It's
activated,
called-
but
it's
I
like when
am
it's
aware of
happening.
yours, yes. And I will have to fiddle with how to make it do that for you. I'm pretty sure I know how.
I finally got
It's like,
after my bed.
right, but there's like a
Like every tutor
specific
session,
user
study
has
session.
different things, option, and I just haven't activated it yet. Because I haven't finished it.
That's what it took.
So, and I will finish it tonight after I figure out if we finish this chapter.
So
So,
much. I wish
it's
I loved
possible
it, but
to request
Because if I left
my accommodations at double time
I
and
have a
a quiet
career as a financial
testing
advisor.
environment.
Quiet's up to you.
If I left now.
Well, I go to the testing center.
Right,
Or a banker.
yes. You choose the environment when it's an online thing.
A chemist. Accountant.
And
Theoretically,
I
no.
don't know.
Asking for it pretty please is not, because I have to, if I did that and then somebody else found out,
Sure.
that would be a problem. But the moment that I do have official recognition, then yes, I will do so. I have no problem with the act of doing so, it is simply a matter of equity.
It got a lot better when I started digging out the value because it wasn't just the ADD, it was the anxiety.
If you do it first thing in the morning tomorrow, then, and then give me the day, so don't take it till Saturday. If I get a letter tomorrow, then yes, I could add it. But
Yeah, I'm going to.
I just don't know how fast they're gonna get around to
Right.
notifying me. And so that's the lag that I can't control.
The lag I think that's the biggest is if it's not payroll.
Right. And so the problem is, even if you start it tomorrow, if they don't finish it by the end of day Friday, I'm not gonna get it before the test closes.
I figured out how to do it when I sent mine, it's pretty quick, they just have to click submit and then they just forward it on there.
I forgot that, I've been out for almost a year and I forgot I actually have to
Did you say at the
re-register
beginning of
with
class if you were able to grade the homework?
Oh, you've never read.
I did grade and correct all the homework, yes.
Okay.
Actually, let's,
I was trying to look earlier to see if I could look at the.
well, because we weren't sure, 55, we're not, we're only about halfway. I need to hurry this up. Let's see if I can reload, what does it do?
That's good, because I didn't.
50% is more.
No, it's horrible, but compared to what I did, that's
Nope,
good.
it still hasn't auto-graded, so I'm gonna have to find out why it's not doing that. So you should be able to go and look at it, but it has not finalized your grade in the grade book, and it should have. So I don't know what I didn't click to tell it to do that.
So once that happens, maybe we'll be able to go in and see.
You
what
should be
we
able to go in and
missed.
see it now.
Well, but I wanna know what I
What you got
missed.
wrong?
Mhm.
That I'm not
Yeah,
sure
it's
of.
not showing that, but it finalized my grade in the grade book.
None of my grades are finalized in the column in the grade book. It's acting like I need to grade them, even though I have graded them.
Oh, huh, that's weird, now it's not.
Right.
It's not right there.
So I don't know what's up with that.
Is there something we could do, extra credit, something?
That's weird, it showed up earlier now.
I know.
So if we don't finish 6 tonight, will that
It will not
carry
be on
over
the
to
test.
the next exam?
It
though?
will, it will.
If we don't finish 6 tonight, then the test will be 50-ish questions over 2, 3, and 4. And the next test will be possibly over 5 chapters instead of 4. So, right, yeah, it's like, there's really not a, like either, there's strengths and weaknesses to both, right? Like, not having it today, you might like, but it means you're gonna have more questions over chapters that are all about math. And it means that you're gonna have more material that you'll need to be able to cover, but fewer questions for each one, but more, so it's like.
You could probably get through 10 pages by 8 or 9 o'clock.
I mean, if we keep going and I don't get too distracted, I think we'll probably be okay.
So no
But
more
it's-
questions, y'all.
Well, but you
I
said that there was
posted
a lot of
a
people
link
who answered some questions.
for
Right, yeah, exactly. I mean, we're
the
moving
YouTube
through, it's just a
list.
matter of,
Okay.
do we get there? That's
And
the thing.
I need to figure out.
right now I'm
Hey, so I emailed.
uploading raw video,
Okay.
you know, not beautified.
About what?
That's
I see you
Work,
have
like the
it,
first time I
Um,
submitted it,
and then
As
so
long
when
as
I
it has the
click on
audio,
your, like on
you know,
the actual biology homepage and I click email
Thank
you,
you.
it won't,
but it's gotta have the
it won't
thumbnail
email
and
you.
the
It said it
face.
sent, but it
I
never
don't guess.
responded.
I don't think I got anything about,
But it did that to my, so I'm taking
What
a
did you
different one
ask?
too. It was
Just-
about my homework.
just a specific question about the homework?
I don't know, I don't remember.
Yeah,
honestly.
I don't remember getting a question about the homework now.
Okay.
But that's the way you're supposed to do it, you're supposed to email
And
me
then your
through
computer
Google
Did you
Drive.
get my
Yeah.
email today?
Layout sequence,
I think, I did
Yeah.
get
Yeah.
it.
try different things.
I almost
And each
emailed
time
you,
you
but
get
I was
done,
already on the way, so I
Yay,
was like, I'll do it 5 minutes.
So like five. I did not take into account that
I took
The target file is
class
supposed to
in
be
high school,
18 gigabytes.
but
From Kelly.
I got a
It
head injury.
creates at least 3
So,
times that amount
I literally,
of
I literally had to read.
I didn't send it from my caregiver, I sent it from my work.
and deleted.
Well, it shouldn't matter which one you sent it from, as long as you sent it to my Cougar. But if I responded, I would have to respond to you in Cougar.
Yeah, it's fine.
So,
His name's been so long.
I think there's like a problem.
Kelly Farber?
Yep.
Yeah, I got that one.
Okay.
But,
It just got pulled.
that's the only student email I have, so I don't know.
Maybe it looks like some problems.
You email me as well?
Yeah, I don't think that it works when you click on his
Email me.
email me.
Yeah, that's what I
It
do.
does not seem to be.
But see, when I go into Cougar Track and I try to put your name doesn't even pop up, so I don't know what the deal with it
I
is.
clicked the email me and it worked. That's how I found it.
Did you click, well, we'll try. We need to figure that out, because you do
Because I
have.
did it to my other teacher too, and she never got it. So I
Yes.
actually went to her email that she had sent me before classes started and then
Responded
emailed
to
her
that.
from that.
Which we could
They're
also,
not in there.
which I could just send an email to everybody, and then you could just reply to that with questions. That would also work. But you should be able to just click on my name on the web page, on the page for this class at a minimum, and it should get to me.
Yeah, that's
Because
what,
that's the whole point.
that's what I was thinking.
So, no, I did get yours about this evening, but, and I got quite a few before class started, but I have not really gotten anything since. No. So we do need to figure that out, because I need to be able to get that so that I'm appropriately assigning attendance and all that jazz. Wait. Are we missing, is Maggie the one we're missing tonight? Yeah, that must be it. Okay, so, because yeah, like I've got it on my phone. It's got its own special little app just for effectively you guys and the boss people trying to email me to tell me what to do. So it's not even like it's getting buried in the 100 emails I get from the zoo every day. It's like, no, it's just all by this one.
Okay.
So do you know if that guy that came in here that does the study?
Tutor sessions, yeah.
Is he not a teacher no more?
No, I think he just runs that study section actually from what he described. I'm not sure. He might.
That was my chemistry teacher before I got
Did you
that.
choose to email us?
Oh,
It was that. Email us as the tutor. No, I talked to him.
As a reminder of that.
Yeah.
Yes, I still have the handout, so I could email you a reminder of the tutoring information.
Okay, that sounds perfect.
Which I could also, I think I have 2 of them up here, so I could also give you a handout if you remember to ask me before you leave.
No, handouts are good. They get buried in purses and
Oh,
backpacks.
yeah, okay. True, I can see that.
On my post app.
Alright, so let's see if we can get through this, and if we can, I can spend some time after we're done, or if we can't, I can spend some time after we give up, talking about the homework and stuff for tomorrow, or for the test this week. So, here's the thing. Molecular compounds. This is carbon dioxide. Now you'll note that we are giving it a name, and now you'll see that little dye in front of it, right? Now when we were talking about our ionic compounds, we didn't give dyes, tries, we didn't name things in terms of numbers as part of the name, because we were supposed to understand that this was an ionic compound, and therefore we should be able to intuit how much of each is there based on our knowledge of the charges of those individual components. When we start talking about covalent modification though, like phosphate, which is a covalent molecule, covalently attached connected molecule, those guys we need to have some way of knowing either by nomenclature or simply because we know what phosphate is, because it has a common enough name that it gets its own special name, that we know what's in that molecule. So, from 6.5, what we're going to be talking about is what the type of things that we're dealing with when we're dealing with covalent modification, covalent bonds. So instead of atoms hanging out with each other because they're attracted to each other as a positive-negative associations, now we're going to be dealing with atoms that are holding on to each other, that are hanging out with each other because they have agreed to share electrons. The goal is still the same, filling up that top shelf, whichever shelf it is, right? making sure that your shelf is full. But it does not necessarily involve the creation of ions. Most covalent molecules are in fact not going to be ionic. They might be polar, there might be some different charges here and there, but they're more than likely going to be neutral in their charge, positive, negative type stuff. Covalent bonds. We're sharing electrons to fill our valence shell. I've already said all this. Moving fast. Ish. When we name this, the first non-metal is named by its element name. The second non-metal is named with the first syllable of its name followed by an "ide" there. So there we have our "ides" again. So that would make me my earlier gonna say yes wrong. When we have a subscript ending two or more, prefix is used in front of the name. So mono, hexa, octa. You guys recognize this, right? Mono, di, tri, tetra, penta. Right? So here's nitrogen, because it's the first one. Dioxide, because there's two of them. Here we have nitrogen with 3 oxygens, so that makes it trioxide. Now this is not nitrate as an ion, this is nitrogen trioxide. Some of our nomenclature here is a bit, when vowels O and O or A and O, what? O and O? O and O and AO?
The first one gets.
Yeah, we omit the first vowel. It's like, if we're naming a molecular compound, mono is usually omitted. We usually don't say like nitrogen monoxide. It's just nitrogen oxide. Nitrogen dioxide, though, if there's 2 of them, we can call it dioxide. The exception here is carbon monoxide. Why? Because carbon monoxide is special. We care about carbon monoxide. Carbon monoxide can... Honestly, I think some of the exceptions are just because it became so common to name things something, even though scientists would say, that's not right, you shouldn't be saying that. Everybody would go, but that's what we call it. If everybody calls it that, then why don't we just call it that? Take your bit. There are other examples of things that are named wrong, that if scientists had their way, they'd be like, you should not call it that. Like organic food. Don't call it that. But no one's going to listen to me, because it's too, everybody knows what organic food is. Here's the thing, the only organic chicken that's not organic is a rubber chicken. And even that would be organic if it came from rubber that actually came from a rubber tree. Dang it, it'd still be organic. I don't care how many steroids you pump into your chicken, it's still organic. But that's not what they mean when they talk about organic chicken. They talk about no pesticides, no herbicides, free-ranging, perfectly all natural, no GMO. Sorry, that's pet peeve of mine. Alright, so what do we have here? Some common molecular compounds, especially in biological systems: carbon dioxide, carbon disulfide, dinitrogen oxide, N2O, as opposed to nitrogen dioxide, which is NO2. Why does the nitrogen come first? Who comes first in the periodic table? From nitrogen and oxygen, who comes first? Nitrogen.
So what do we call the nitrogen oxide, nitrous oxide?
Nitrous oxide. I don't know, the same way, why do we call the stuff that you put in cars that blows out the engine and makes it go faster, we just call that nitrous. That's not nitrate. I don't know what nitrous actually is, other than the thing that Fast and the Furious has taught me. It's the stuff you push in the thing to make your car go faster. And video games have taught me that that also damages your engine.
How education?
Yeah, exactly. The things we learn from TV and games. Not always correct. Frequently wrong. Sulfur hexafluoride. 1 sulfur, 6 fluorine atoms. Don't try and count the ionic charge of this, because that's not the point. This is a covalently modified, covalently attached molecule. That is 1 sulfur sharing electrons with 6 other fluorine atoms. Not necessarily all of them with the sulfur, I should point out. But they're all sharing electrons with each other, forming one molecule where you cannot remove something via ionic interaction. Covalently attached atoms. Sulfur trioxide, manufacture of explosives. Lots of fun stuff. What's this? What's the first one? Nitrogen? Tribromide. Tribromide. Right? Nitrogen, no prefix. Bromide, but there's 3 of them, so we give it a prefix of tri. So we use the first nonmetal, comes first. Bromide with the first initial followed by I, bromide. Nitrogen, tri-bromide.
But see, Br is bromine, so then you have to add the IDE also?
Right, so you take the first syllable, bromine, brome, make it I instead, bromide. Using the first syllable of its name followed by ide. So that would make something Americunium would be something other amoride, right? But you're never going to see that because Americunium doesn't last very long. But like, that's an example of where the nomenclature is a little weird because like, yeah, but amoride for Americunium, that was first syllable plus ide. What's the molecular compound for diphosphorus pentoxide? P2 for di, right? Four is tetra. Pent is
8. No.
5.
P2O5. Now, once again, this works. This nomenclature works when we're talking about relatively simple molecules. We get into the organic chemistry portion of this class, and the nomenclature is just going to explode. I'm just warning you. But that's like last third of the class. No. You signed up for it. It's in the learning objectives. Besides, that's where the fun stuff happens, is in the organic chemistry. A compound is usually, here's some rules to tell the difference here. It's usually ionic if the first element is a metal, like NH4. What's the name that we gave to that NH4 ion? Ammonium. K2O, K is a metal. Potassium oxide. There's our ionic potassium oxide. It's molecular if the first element of the formula is non-metal, like nitrogen, carbon, phosphorus, sulfur. Once again, when we go through this on the quiz or on the test, this is going to be multiple choice. So find the answer that fits. Look up the rules if you need to and find the answer that fits. Here's the flow chart. This might be handy. It's a lot of information in one slide, right? I don't know if it's actually handy. You'll have to tell me after the test if it was handy. Flowcharts are really useful for some people, really not useful for others. It just... All right, 6.6. We've got to get from 6.6 to 6.9. Lewis structures. We're talking about covalent modification here now. So, these dot structures, we've seen that before, right? What do the dots symbolize? What do the dots represent? The books on the top shelf, right? The valence electrons, right? And because we're keeping things simple for this class, what's the number of valence electrons that fit around any given atom? 8, right? That's where the octet rule comes from, at least as far as we're going to apply it. Now, that means that we can draw it like this. How many electrons does carbon have? Look up there, it's in period, it's group 4, so how many valence electrons does it have? 4. Because it's in group 4, that means it has 4 valence electrons. Lithium has 1. What does it be? Beryllium? Be? What was that? Beryllium? Beryllium? Yeah. Lithium has 2, boron 3, carbon 4. So, why do we have 8 around it? What do each of those hydrogens bring? They bring 1 electron, which means that that carbon is surrounded by how many electrons? All 8. That makes it happy, right? That makes it stable. Why is the hydrogen happy when it only has 2? How many shells does that hydrogen atom usually walk around with? 1. Just 1. And how many electrons fit on that first shelf?
2.
Only 2. So that hydrogen is perfectly happy sharing 1 electron with the carbon because the carbon's sharing 1 electron with it, and since they're sharing, they both get to count it. So the hydrogen says, look, I have 2! And the carbon, because he's got 4 hydrogens around him, is saying, look, I have 8! And everybody's happy. If we wanted to name this carbon tetrahydride, we wouldn't call it that. What would we call it? We wouldn't call this carbon tetrahydride because it has a very special name, especially when we talk about organic chemistry and fuel. We call it methane. Methyl. CH3 is a methyl group. CH4. Alright, what about this nitrogen right here? That nitrogen has how many electrons around it?
5.
Well, nitrogen over there, normally it starts with 5, yes. So how many electrons does it need to make 8? 3. That is why it is sharing with 3 hydrogens. So if we were to draw the dots around that nitrogen, the first 4 would go 1 on each side, and the 5th one would go, pick a side, it doesn't matter, right? And so that would mean that we would need 3 hydrogens to share on the 3 sides that only had 1. And that would once again give us nitrogen with 8 around it, and 3 hydrogens with 2 for them, so everybody's happy, and that makes it a stable molecule. What's the polyatomic ion that we're used to talking about? Not NH3, but what? NH4. And what's the charge? +1. How could we get that? Do you see it? Let's take a hydrogen ion. Just a proton that doesn't have any electrons to play with. What if it comes up and says, hey, Mr. Nitrogen, you've got those two electrons right there, and you know, nobody else is sharing them with you. Can I just kind of hang out next to that and maybe sort of share them with you a little bit? Is there room for it to fit there? Yeah? Is there another atom occupying that space? No. Now, could a regular hydrogen atom come in and do that? Not if it has its own electron already. Because that would mean that the nitrogen would have 9 electrons surrounding it, and that would not work very well, would it? but a hydrogen ion could, H plus could, and what would that make the overall charge of that NH4 polyatomic ion be? +1. Oxygen combined with 2 hydrogens. Once again, if we wanted to, we would call that what? Oxygen dihydride? Maybe? We don't call it that. What do we call it? H2O or water, right? Dihydrogen oxide, I guess, H2O.
The hydrogen monoxide is the one they use for the.
For the side of the thing that nobody understands, they're just talking about water. The threats of dihydrogen monoxide. Oxygen, over there in group 6, how many electrons does it need to fill up its outer shell? 2, right? So if it shares electrons with 2 other hydrogens, it has 8. And those hydrogens have 2. Now, that's the Lewis dot structure, but we can also take all of those we can take those pairs of electrons on one side. So those 2 guys right there, that is the bond that is shared between that carbon and that hydrogen, we can write it a different way with a line. And that signifies that it is a single bond. That means that both of those atoms are sharing 1 electron each with each other, forming a single covalent bond. Which means all of those hydrogens are attached to that carbon via a single covalent bond. It means all of those hydrogens are attached to that nitrogen via a single covalent bond each. If I'm going to name them by specifically calling it a single covalent bond, that implies that there is something more than a single covalent bond. Otherwise, I would just say that there are just all covalent bonds, right? We can get double covalent bonds. We could even get triple covalent bonds. We could even get sort of. You can't really get a tetra bond. Well, not with carbon. You can get really weird bonds later, especially with some of these transitional elements that get to be really hokey with what you call a valence electron, right? We're not going to worry about that. I'm just letting you know it can get hokey. Here's a space fill model instead of the Lewis dot or the stick model. So here we have our central carbon surrounded by 4 hydrogens. Here we have our central nitrogen surrounded by 3 hydrogens. Here we have water surrounded by 2 hydrogens. I want you to notice something. Take a close look at the difference between the methane space fill model and the ammonia space fill model. Because we're going to get into this in a minute. What's the difference? There's something missing in that ammonia model at the top, right? Now, why is it that those hydrogen atoms are spread out like that around that carbon? Because those hydrogen atoms are carrying electron density. So they have their positive proton center. There's electron density between them and the carbon, and so all of those negative electrons, they don't want to hang out really close to each other, right? They want to get as far apart from each other as they can around the surface of that atom, and they will do so by forming a very specific orientation, which we will give a name to here in a minute. Why don't those 3 hydrogens, why are they all on the bottom like that? Doesn't that mean that they're closer to each other? Like, because they're not just on the side, right? They're not just like blip, 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 on the side like a plane. They're below the plane. They're all below. If you were to cut that atom in half, sort of like that, they'd all be below the cut. Why? Do we have some negative density right up on top here that's pushing them down? Just like we had some negative density right up on top here with that hydrogen that's pushing them down? Yeah, we do. That electron pair that's not being shared with anyone else because it's already a pair, they're sitting right on top of that dot. We don't draw them in a space fill model, but they're there. And that's why those 3 little white dots are not on the side of the blue ball, they're down near the bottom, just like they are around that black ball. Because there's still electron density, there's still negativity that's forcing all of those other pieces to move in certain directions. And that is because we are single bonding all of these molecules. If we start talking about double bonding, the jig is off. Other shapes start applying, and we're not going to get deep into the hybridization things, and I really wish we did, but we're not going to. So, covalent bonds is when we share one or more electrons with another atom. And this second bullet point here is kind of important. Valence electrons are shared by non-metal atoms to achieve stability. Metal atoms are nifty in the way that they form their lattice structure and their crystals, which is why when we talk about ionic crystals, it almost always, if not does, always involve a metal of some kind. Metals don't have to form ionic bonds to pair with each other. They're weird like that because of the way their electron density works out. Like a big chunk of copper, a big chunk of iron, that's not a whole bunch of iron molecules covalently attached to each other. That's just a whole bunch of iron molecules just hanging out like so, just chilling. But non-metal ions, non-metal atoms, excuse me, will form covalent bonds to share electrons to fill up their outer shells. What's the thing about non-metals that makes them so different from the metals over here on the left, other than the shiny bit and the ductile bit? What's one of the major properties of metals that we use them for, that we find them so useful?
Conductivity.
Conductivity. What do nonmetals not do very well? They don't conduct very well. That's because in our nonmetals, when we're combining them together, we are forcing those electrons into very specific relationships to form those covalent bonds. The reason that the metals, whole metals, conduct electricity really well is because their electrons don't really have specific places. They can shift anywhere and all over the place. That's what electricity is literally the flow of electrons. From one atom to the next, 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 to the next. These guys, these nonmetals, they don't conduct very well. Especially in compounds, because we have locked their atoms into place via covalent bonds. Hydrogen. Normally when we talk about hydrogen having one proton and one electron. But that is not stable, because its shelf, oh no, is not full. Can we still work? Did I break it? No, I didn't. Good. Its shelf is not full. But if it shares its one electron with another hydrogen, now both of their shelves are full. This is why hydrogen as a gas is never found as H. It's found as H2. Chlorine, bromine, iodide, as in their natural occurring state, as a pure element, what shape, what form do you think they're going to take as well? They're missing one electron to fill up their outer shell. So just like hydrogen only needed to share one to fill up its shell, what if each of them, what if chlorine and chlorine decided to share one electron with each other? How many electrons would there be around the outer shell of each? 8. The halogens are usually found in diatomic atoms, or diatomic molecules. 2 of them. H2, Cl2, Br2. Now you can find them individually in molecules where we've covalently modified them, broken up that pairing. You don't always have to have 2 bromine molecules, 2 bromine atoms in every molecule. You can have just 1 bromine. But if you're going to talk about pure bromine, you're talking about Br2. If you're talking about pure hydrogen, you're talking about H2. Why are we not also therefore talking about Li2 or Na2 or K2? Because even though hydrogen's over there all the way on the left, what do we call everything beneath it? Metals. And what do they look like at room temperature? Solids. What's hydrogen at room temperature? A gas. Very different. Here's the thing. Two hydrogen atoms that are far apart with only one electron, the energy level that those hydrogens have is rather high. The reason why they share, and this is a conceptual graph here, but this is foundational. So I'm going to spend a minute harping on it. Hydrogen atoms that are individual and separate have much, much more energy than a hydrogen diatomic molecule. In the same way that water at the top of a dam has much, much more energy than water at the bottom of a dam. And the thing about all of reality, and I realize I'm bringing in a player here that this book is trying to avoid, but entropy is not a nice guy. And entropy is part of a physical process that says every atom will seek to find the lowest potential energy state that it can occupy all the time. And that is why you do not find hydrogen atoms floating around with one electron by themselves. Because entropy will them every time it finds one and says, "Go get it, friend!" Because you have too much energy. Now we can force them to be alone. And what does it take to do that? A lot of energy. You guys remember chemistry? Like, did you take a chem lab in high school? What did you have to add to almost, not all, but almost every reaction that you ever played with, messed with in chemistry class?
Water.
Sure, most reactions are aqueous. Past that, what was beneath the water?
Heat.
Heat. It's a lot of math.
Yeah.
A lot like this chemistry class. This is foundational. It's also conceptual. The reason why you find these hydrogen atoms in this configuration is because that's the lowest energy state that they can find. If you could provide a way for them to get even lower, they would do it. And you wouldn't have to do anything to help them, other than provide them that opportunity. They would do it. Now, to get them to go the opposite direction, you have to force it. Forming these bonds makes them have a lower energy state than what they started from. Plants take hydrogen from water, oxygen from water, and carbon dioxide from the air, pretty much just carbon dioxide from the air and hydrogen, and they combine it into sugars. But what does it take to do that? A whole bunch of sunlight, which means a whole bunch of energy. What do we get by burning the sugar that we get from plants? A whole bunch of energy. Lewis structure. You want to arrange them to give octets, except for hydrogen, because once again, that first shelf only has 2, right? So, our shared electrons are bonding pairs, 2 dots, or a single line. Non-bonding pairs, or otherwise known as lone pairs, are just placed on the outside somewhere, it doesn't matter where. So here we have fluorine. We've lined them up to make it really obvious that they're going to orient themselves in this manner. And they will come together to react to form that structure there, which we could draw like that with a dash instead of just 2 shared dots. We could also represent that just by F2. And if we used a space fill model, it would look like that. 2 big circles that are together. Yes?
What about the noble gases, like helium and stuff like that? Do they fall into that category as well?
Well, what category? What do you mean?
Like the...
Always being diatomic? Why would they? The whole reason why hydrogen is forming a diatomic molecule is because it needs to share electrons to fill up its shelf.
Okay, so those don't need to...
Yeah, their shelves are all full.
Okay.
So they're just there. sitting there, being all noble. These are the guys that exist as diatomic molecules. What do you notice about the state of all of these things at room temperature? Gas. Okay, fluorine makes sense. They're sharing one electron. What would oxygen have to do to fill up its octet so that both of those oxygen molecules had 8? What would they have to do? So here's our oxygen. Here's our oxygen. Each one has how many?
No,
8.
We want 8. Each one starts with
5.
5.
No, it's
6.
6. It's in group 6, so it starts with 6. 1, 2, 3, 4, 5, 6. You see how I'm drawing it? I'm not drawing it vertical. I'm like tilting it off, 45 degrees. Follow? 1, 2, 3, 4, 5, 6. If we share this guy and this guy, how many would each of them have around them? 8. That would not be a single bond. That would be a double bond. All right, let's take that lesson and ask, how does nitrogen form a diatomic molecule? It starts with 5. So what would it have to do? I'll give you a hint. It's really hard to draw with a Lewis dot structure. It needs 3 more. Each of them needs 3 more. So what would it have to do? To get 3 more, it'd have to share 3 of its own, right? So that would mean that that nitrogen, that N2 right there, how many bonds? It's not a single bond, it's not even a double bond, it's a triple bond. This is why, even though nitrogen is 70% of the atmosphere, plants need nitrogen for fertilizer. Why? It's 70% of the freaking air. Can't they just take it from the air?
Has to be fixated.
We have to fix that nitrogen, and that's a nifty term that we use to describe what? Taking that N2 and breaking not just 1, not just 2, but all 3 of the bonds that's holding it together, so that we can get a nitrogen molecule that's available to incorporate into biological molecules. Guess how easy that is? The answer is not easy.
It's from bacteria.
Certain bacteria, certain quite a few fungi. Most organisms can't fix nitrogen. Even though you breathe it in every moment of your life, 70% of the air around you, you butt kiss with it. There are states that are thinking about using it as a method of execution. A gas chamber with nitrogen. Put a man in a room, fill it full of nitrogen, and watch as they suffocate. Because there's no oxygen. It's one way to kill somebody.
That's cool.
I mean, we could that, or we could shoot them in the head, or we could inject them full of drugs that have expired and no one will sell it in the States, which is why there's this issue. But that's politics.
They should start nitrous oxide, laughing,
Yeah, there you go.
die
Well,
laugh.
that's the idea behind some of the drugs, is let's knock you out first and then kill you. The problem is getting the drugs, keeping them on. That's why there was a month ago, there was a state that was trying to kill like 5 people. Like, do it fast, do it fast, do it fast! Because somebody realized, holy sh, this drug expires in a month. And you can't use expired drugs to kill people. That would be inhumane. Right? I don't want to get too deep in the politics. I'm just throwing it out there. You guys can argue with that over coffee. Because you're college students, you stay up all night drinking coffee, right? All right, let's keep going. So, drawing Lewis dot structures. Here's our carbon with 4, here's our hydrogen with 1. We put them all together to form that nice little methane. And that gives all of these guys the electrons that they need to be nice and stable and happy. You've seen this already. Methane, ammonia, water. what's different about that water molecule and that methane molecule? Remember I told you that that ammonia molecule is just missing that little white dot at the top, but it's still, the reason that those two balls are pushed off to the side and down, right, is because we have those two dots are still there. What about oxygen? Why are those two hydrogens pushed off to one side? Because guess what we have? We still have 4 sets, right? They're just 2 lone pairs. But they are still negative, and they are the things pushing the 2 hydrogens to one side.
So is ammonia at all considered polar like water is?
Yes. Well, yes.
That's why it's reactive.
Hmm? Which will, if you don't understand that question, we'll get to it. Hopefully soon. So, a double bond, we've mentioned, that's when we share more than one pair, right? If each atom is sharing 2 electrons instead of just 1, it's a double bond. A triple bond is when we're not just sharing 2 atoms, or excuse me, 2 electrons, but 3! There's your triple bond. Draw the Lewis dot structure for carbon dioxide where the central atom is carbon. So, how many electrons does carbon have around it? 4. Carbon is in group 4, so it has 4. 4 valence electrons, which means we would draw the dots where? How many on each side? 1 on each side. Oxygen is in group 6, so it has how many valence electrons? 6. So it would have 2 lone pair, right? Because we put 1 on each side to get 4, and then we put 2 more dots on 2 sides to fill it up, right? So we have 2 lone pair. Those guys are not going to get involved in this. Because they're already paired up, right? But oxygen does have 2 single electrons, right? So it's going to share both of those electrons with our carbon. Each of them is going to share both of those electrons with our carbon. So what's that going to look like? How many bonds are involved here? 2 on each side. Here's all of that we just did, written out. Valence electrons 4 here, valence electrons 6 here. They're totaling them up there, because that's nifty. I don't know what you would actually, I mean, that's a nice number to have, sure. I don't know if we're actually going to use that here in a second. So here's what we have. Our carbon, all 4 electrons are being shared with oxygen. A double bond. A double bond right there. Why is that? So we've drawn this up here. We're going to attach one single bond, so we have oxygen attached with a single bond to carbon. Why are we not done? Let's walk through it the way they're walking through it. Attach each bonded atom to the central atom with a pair of electrons. Right. Carbon still has another atom, another electron on top and on bottom, but it's so there's 2 more that aren't paired up, right? There's one right here that's not paired, one right there that's not paired, right? And oxygen has the same problem, right? It's got 2 lone pairs out here, but it's got another one on both sides that aren't paired. So what do we have to do to make sure everybody has 8? We have to share that extra set to form a double bond.
Where do those come from?
They're coming from the dot structure that we have out here. So here, let's draw it.
Okay.
So, oxygen, carbon, oxygen. So I'm going to tilt this like this. I'm going to tilt this like this, just so that you can see what I'm doing, right? So oxygen has 1 here and 1 here, and over here it's got a double and a double. You follow what I meant, why I tilted it, right? Same thing over here, we'll have a double up here, a double over here. We'll have 1 down here and 1 on this side. Now carbon has 4. 1 on each side. So we can share one of them So we're now linking these two right here and these two right here. That is what happened right there. They're just not drawing all the dots for you. All right? But that means that these two count over here, but now our oxygen only has 7. And this oxygen gets to count that one, but that means it only has 7. And this carbon gets to count that one and this one, right? So if I draw a little arrow down here just to give us the carbon, that carbon would look like this. There's 2 of them there. Actually, let's put them on top because that's where I drew it. 2 of them on top. There's 2 of them on the bottom, right? But we have one on the side here and one on the side there. That carbon is not happy yet. What would it need to do to get one more electron on both sides to fill it up? Well, it needs to share another electron. Conveniently enough, both of those oxygens have a spare, don't they? So this guy can get shared with that. This guy can get shared with that. And now we have formed, now what's happened to that carbon? It has all 8, it's happy. We would draw that as a double bond, like that. A double bond between both oxygens and the central carbon. Each oxygen is sharing 2 electrons with the carbon. The carbon is therefore sharing all 4 of its electrons with someone else, split evenly between the 2 oxygens. Does that work?
No. Because the carbon has 4 because it's like, is it because it's a 4-way percent and...
Carbon has 4 because it's in group 4. And it wants to get to 8. Right?
Yeah.
It has 4 valence electrons.
But hydrogen only has 1.
Hydrogen only has 1.
So if you do 40 between that, you don't need hydrogen. You just need C2.
Let's erase those carbons. Alright, and now let's focus on this carbon right here, right? So that carbon right there, see, I'm blocking it for a minute. That carbon right there has 3 bonds. It starts with 4, right? 4 electrons. We're sharing 3 of them with someone else, right? So let's write in our shared ones with S's. We're sharing this one here, that gives us a pair, right? We're sharing this one here, that gives us a pair, right? We're sharing this one here, that gives us a pair. There's our triple bond with that other carbon. Do we have 8 yet? No. We need to share that one right there with somebody too, don't we? Well, who's a convenient guy to bring along just one little extra electron?
Hydrogen.
Hydrogen. So yeah, that is an example of a perfectly valid organic molecule of 2 carbons triple bonded to each other and 1 hydrogen on either side. And if you followed all of that by using the Lewis dot structure, then good, you're picking this up. It is simply a shorthand to help you count the number of electrons. And with the exception of hydrogen, everything else wants how many? 8. And you will form as many bonds as is necessary to get 8.
I thought fluorine, you could only do like 2 and stuff like that. Or is that?
Fluorine, okay?
Or oxygen.
Oxygen, we did oxygen, but let's do fluorine. So fluorine has how many electrons? 7. 1, 2, 3, 4, 5, 6, 7.
Oh, okay. I see it now.
We're missing one. What could we do? Well, we could bond with another fluorine that has 1 there, but all of the others. Well, sorry, shouldn't confuse you. 1 line, right? Single bond. Not everybody has 8. And we're happy.
And how would you write that?
How would I write that? Well, you could write it like this.
The F2?
Well, yeah, just F2.
Okay.
Yeah. Yeah, F2. Just like H2, Cl2, Br2, I2.
So
Yeah.
other than hydrogen, everything else is A?
Yes. Hydrogen is weird. Technically helium is also weird, but helium we don't worry about because it's a noble gas. But the reason it's weird is because that first shelf, that n equals 1 for the quantum state, that bottom shelf only has room for 2. Everything else has room for, let's say, 8 in air quotes, right? Because 4 and up, a lot more than that. So does this make sense? Do we all follow how to do that? We're probably not going to finish this.
You're not.
Exceptions to the octet rule. While the octet rule is useful, hydrogen requires just 2. The noble gases are weird. They don't do anything. Non-metals like potassium, sulfur, chlorine, bromide, iodine, they can form compounds with 10 or 12. So the octet rule works except when it doesn't. And that's why the octet rule is a very simple way of modeling bonds. Some of these guys are weird because their valence electron... Effectively what happens is some of those books on the lower shelves, if you give them enough reason, they'll start sharing with other things too. Instead of just the books on the top shelf, some of those lower shelf electrons will also be able to be recruited into bonds. We're not going to talk about the whys, but here's your exceptions. So these guys are weird, and sulfur is weird, which is how you get SF6. Because sulfur can have up to 12 valence electrons and still be handy, still be comfortable. So these are exceptions. What do you have to do with the exceptions? You just have to know them. Or know where to look it up. Exactly. Chapter 6 is a big chapter. It's okay. If we don't finish it, that's fine, because octet rule is it's very simple, but it is a good way of learning how these things are put together, how we start building simple molecules. But let's see if we can get through this. Electronegativity. This is another characteristic of atoms, just like atom size, right? Or ionization energy, right? Electronegativity is something that we haven't defined yet, but we will in a second. But we're showing you that electronegativity is increasing as we move through the period, and it is decreasing as we go down. What is that the same as? That's the exact same behavior as what?
Ionization.
Energy of ionization, yes. That's because electronegativity has everything to do with something sort of like ionization.
The electronegativity value of an element indicates the attraction of an atom for shared electrons in a bond.
It's high for nonmetals. Fluorine is the highest. Why would that make sense? Look at this rule. What is the furthest right and furthest up?
Chlorine.
Fluorine. So it is the highest. What is electronegativity? What I should before we answer that question though, what's the next nasty next to fluorine? We got two options: fluorine and oxygen. Right? Oxygen, very common in biological molecules, does not play well with others. Very high electronegativity. Nitrogen's right next to it, but it's a significant drop down. But it is also fairly high with its electronegativity. So, let's learn about what electronegativity actually is. We know that it increases and decreases the same way as energy of ionization, right? Once again, here we go. So here's our electronegativity. 4.0 for fluorine, 3.0 for chlorine, 3.5 for oxygen, 3.0 for nitrogen. All the way down here, what's the lowest left and bottom left? The lowest one, 0.7. Hydrogen has a nice little 2.1. Now, what are you going to do with these numbers? These numbers give you the relative ratio with which an atom is going to hold on to its electrons. So, if you're grouping hydrogen that has a strength, if you will, of 2.1, and you're pairing it up with the fluorine that has a strength of 4.0, who's going to win in that arm wrestling match? Fluorine's going to win every freaking time, right? That's what electronegativity is. If you're dealing with, say, a carbon and a hydrogen, 2.1 to 2.5, is that going to be more of an even match? Carbon's going to win, but he's not going to blow the other guy out of the water, right? Carbon and hydrogen bonds are relatively equally paired. If you were to look at where the electron is between a carbon and a hydrogen, it's going to be right about in the middle. That's a gross oversimplification, but it works for illustration. All right? But if you were going to look at where a hydrogen is between a hydrogen and a fluorine atom, where's it going to be? It's going to be really close to the fluorine, because fluorine will grab that electron and hold on to it really strongly. And the hydrogen just can't keep up. So, what this does is it creates polarity of bonds. Now, if you have two hydrogens pairing with each other, this is not polar, because the electrons are shared perfectly equally. Because one hydrogen ion has exactly the same electronegativity as another hydrogen ion. But if you pair that hydrogen with chlorine, which had a strength of what? 3.0? Not quite as much as oxygen, the same as nitrogen, right? That means that that electron is going to spend a lot more time, it's going to be a lot closer to that chlorine than it is to the hydrogen. Why do we care? What does an electron bring with it that we've been counting over and over today? A negative charge, right? And if that negative charge is hovering perfectly in the middle between two positive charges, then it doesn't matter. But if that negative charge is hovering around the chlorine a lot more than it is the hydrogen, then that means that even though this is a covalent bond, most of that negative charge is actually going to be on the chlorine. And so that means that the hydrogen is going to have a lot less of that negative charge, which makes it kind of what? Positive. This gives us polarity. So even though it is not an ionic bond, it is acting kind of like an ionic bond. Because we have a positive and negative charge here. Not a full charge. It's not full plus 1 and full minus 1. It's less than that. But it is there. And what do we know about positive and negative charges? They attract to each other. Now these two right here, they're already attracted to each other. They're sharing electrons, if somewhat unfairly. But that negative chlorine, is it going to maybe feel like it's being, like it could hang out with a few other slightly positively charged hydrogens? Because the chlorine's a little negative and those hydrogens, they're a little positive, and so maybe you could hang out with them too? Because positive and negative charges are attract, right? Nonpolar covalent bonds are bonds that occur between atoms where they have an equal electronegativity. So a nitrogen bond right there is going to be nonpolar because it shares it evenly. A chlorine bromide bond is going to be not very polar, not polar at all, 0.2, nonpolar covalent. Hydrogen silicon, 2.1 to 1.8, not much of a difference, pretty much nonpolar. We get up to 0.5 or above as a good rule of thumb. A difference, so if we get oxygen and chlorine, 0.5, this is polar. Who's going to be more negative here? Oxygen has a 3.5, chlorine has a 3. Who's holding on to it tighter? Oxygen, because its electronegativity is higher. So that's polar. The oxygen's going to be a little bit negative, and the chlorine's going to be a little bit positive. Oxygen, sulfur. Oxygen's 3.5, sulfur is 2.5. Oxygen's going to be quite a bit more negative. Sulfur's going to be quite a bit more positive. As these bonds, as we get bonds between atoms that are more and more different in their electronegativity, we start creating polar covalent bonds. Those polar bonds create what we call a dipole. Polar bonds, dipole. Why do we call it a dipole? You ever seen a magnet with a north pole that didn't have a south pole?
Not very big one.
Next time you break a magnet, try this. It's one of those things that they tell you, but it's hard to actually discover it until you discover it and then forget. It's like, wait, why is it? Take a magnet and break it. And now try and force that magnet back together again. Like, oh, I just broke my pencil. I could glue it back together, right? You take a magnet, perfectly happy being a magnet, right? Sticking out, here's your north pole, here's your south pole. You break that thing in half, you try and glue it back together again, it's not going to work. Because the moment you broke that magnet, you just created a new north and a new south pole. And they are aligned with each other. You will not get those two magnets back together again. Every polar object, by definition, is going to have a positive and negative side. You can't have a positive end without a negative end. That's what a dipole is. Two poles. One of them positive, one of them negative. Why does it matter? Because positive and negative forces attract, right? And negative negatives repel, positive positives repel. We can draw an arrow that points from the positive to the negative end, just as a general rule of thumb of association, so that we can show which one is more electronegative, if we want to. Ionic bonds occur between metal and non-metal ions. It's a result of electron transfer. Why is that electron transferring? What's the electronegative difference between chlorine and potassium? Chlorine's 3.0, potassium's 0.8. Why is it that our ionic compounds was always an association between a metal and a non-metal? When we're talking about lithium, sodium, potassium, they want to give up an electron, right, to fill that outer shell? That's true, if we want to anthropomorphize a little bit. But it's not really that they're giving it up. They're associating with something else like a chlorine atom, and that chlorine atom is just quite literally ripping away their electron. Instead of sharing it together, it is sticking to that electronegative guy so hard that it loses connection with the guy that it came from. Oxygen, fluorine, chlorine, these really electronegative guys over here on the top right, they are literally stealing electrons from these metals because of the difference in their electronegativity, creating ionic instead of covalent bonds. So, rule of thumb, if the electronegativity difference is less than 0.5, so 0 and 0.4, it's nonpolar covalent. Yeah, it might favor one side or the other, but not enough to really create a strong dipole. If it's between 0.5 and 1.8, it is covalent but polar. If it's 1.9 to 3.3 or higher, the bond is ionic. One of them is pulling so strong that it just rips it right away. Yeah, I've just got 30 left.
We should just start talking about this.
Oh, really?
You should do it, guys. 80%
math, go ahead.
80% math.
Yeah, that's true.
Like, what's important about this chapter 6? Is it more towards the end?
Well, I mean, there's gonna be questions from every section.
I figured. You think it's more
Where were we
complicated?
at, 80 something? 88? Let's see where we get. So here's your rule of thumb. So remember when I said, is there gonna be math on this one? Basic, this is addition, subtraction, right? But there could be questions like, find the polar covalent bond out of this list. Some of which you could rule out pretty easy, based on where they're located, right? In order to be polar, what do you need? You need a covalent bond between something kind of on the left, something kind of on the right. So is a fluorine bonded with a chlorine going to be a polar bond? No.
Wait, what?
Fluorine bonded with a chlorine?
Oh, I thought
We can actually do the math. What is it? 3 and 3.5? I guess that would technically be right at 0.5, wouldn't it be?
Wait,
We go all the way back to here.
how'd you get 3.5?
4 and 3.5, or 4 and 3, fluorine bonded with a chlorine. That would actually be a 1. So yeah, it'd be polar. It'd be a polar covalent, right?
Well, if it was fluorine and oxygen,
Fluorine and oxygen would also be
that would be.
0.5.
Why'd you say it was?
Like these guys here. What if we did a phosphorus and arsenic?
No.
No. What if we did one of these and one of these? That's not even polar anymore. That's what? Ionic. So here's that difference. Here's your dipole. Here's what we have when our electronegativity is shared evenly between our nuclei. Here's what happens when it's shared unevenly. The majority of that negative charge is around one of those nuclei.